Okay, welcome in. This lecture is going to be on Module 11, which is chapters 10.2 and 10.4. So let's get to the start and begin. So 10.2 is triangles. So a triangle is a closed geometric figure that has three sides, all of which lie on a flat surface or plane. So it's a two-dimensional object. If you start at any point and trace along the sides, you end up at the starting point. That is a closed geometric figure. If you have to take your pen or pencil off the paper to get back to that starting point, it is not closed. So Euclid's theorem was that a conclusion that is proved to be true through deductive reasoning. And his assumption about parallel lines is given a line and a point not on the line, and one and only one line can be drawn through the given point parallel to the line. So that is to say, if I have a line, if I can make a straight line, I can't, but there we go. If I have a line and a point, there's only one other line that'll go through this point here that'll be parallel to the other line. If I try to draw and say, oh, it's got to be that one, well, it's not, because those two are going to intersect. There's only one that goes through that second point. Euclid also has in his theorem the sum of the measures of the angles, the three angles inside any triangle is 180 degrees. Right, so in this case, angle 1 plus angle 3 plus angle 5 has to be 180 degrees. And there's a proof here. Proof here says angle 1 has to be equal to angle 2, and that's by the interior angles theorem. So those two have to be equal. And 3 and 4 have to be equal for the same reason. Let's say this 3 and this 4 have to be equal because they're alternate interior angles. And then 2, 5, and 4 form a straight line. So that is these guys right here. They're all on this line, the other side of this line here. They form a straight line. And since 2 is equal to 1, 4 is equal to 3, then 2 plus 5 plus 4, angle 2 plus angle 5 plus angle 4 is 180 degrees. But angle 2 is equal to angle 1, so I can replace that. And angle 4 is equal to angle 3. And so these must equal 180 degrees. So if I have, say, a triangle here, I've got an angle of 120 degrees here, an angle of 17 degrees here. We can figure out this unknown angle by saying that unknown angle in degrees plus 120 degrees plus 17 degrees has to be equal to 180 degrees. We'll call it angle A rather than a question mark. And so we'll say angle A plus that 120 plus 17 equals 180. I can combine 170 and 17 to be 137, and then subtract that from 180, and that angle must be then 43 degrees. So we're asked here to find the measures of angles 1 through 5, right? Angle 1 should be fairly easy. It's 90 degrees because I have these two lines. Where did my thing go? These two are perpendicular lines. I can't erase that. That's no fun. So 1 by interior angles has to be 90 degrees, and therefore angle 1 plus the measure of angle 2 plus the angle measure, plus 43 degrees is equal to 180 degrees. And so that is to say 90, and they've done it here, so I'll stop writing it. But 90 plus the angle of measure 2 plus 43 then has to be 180. 90 and 43 is 133, which I'll subtract from 180. And I get 47. But I know angle 2 now is 47, and therefore angle 3 is also 47. And if angle 3 is 47, I think they do this on the next, yeah, they do. Angle 3 plus angle 4 plus 60 inside this triangle, they all have to be 180. But we just found that angle 3 is 47. So 47 plus 60 is 170, or sorry, 107, which I will then subtract from 180, and I'll find that angle 4 has a measure of 73 degrees. But now angle 4 and angle 5 are supplementary. No, they're not. I always forget these two because I never use them. They are supplementary. Yeah. Complementary is they add up to 90 degrees. Supplementary is they add up to 180 degrees. Right? And so because that for angle 5, they equal 180, but I know angle 4 is 73. So if I subtract that from 180, then I have angle 5. So we have some types of triangles here. An acute triangle is a triangle where all three of those angles are smaller than 90 degrees. A right triangle, you'll have one of the angles being 90 degrees, right? And it's impossible to have two angles being 90 degrees because it's impossible to create a triangle with that. Then we have an obtuse triangle. An obtuse triangle is one who has a very large angle, an obtuse angle, one that is greater than 90, but obviously would have to be less than 180. Isosceles is when we have two sides with equal length, and a lot of times we'll just denote that with a little mark on the two that are the same. And they'll also oftentimes denote then that the angles opposite those would also have to be the same by sometimes throwing a mark through them, sometimes throwing just one angle indicator or two angle indicators through them. An equilateral is one where all three are the same, so we have marks on all three sides. If that is the case, then the angles would also be the same. And very specifically, if they're all the same, they have to be 60 degrees. And then a scalene is where no two sides are equal in length. So I have a side here, a side here, and a side here. I would indicate that they're different by different markings, but also that my angles would be different. So angle 1, angle 2, angle 3, right? They're all different. Similar figures are figures that have the same shape but not necessarily the same size. So like a similar triangle, I'll see if I can do this. Chances are I can't. But if I have, say, that triangle and then that triangle, which is a little bit bigger, right? This angle is going to be the same as that angle. This angle here is going to be the same as that angle here. And this angle here, I'll just put a tick mark through that one, is going to be the same as that one there. That's what makes this a similar triangle. These triangles have what's called corresponding angles. That's where this angle right here, oh my gosh, why does this thing hate me? And that angle right there are the same value, right? So those are corresponding. These two up here are corresponding, and this last one here corresponds with that one. And then we would have corresponding sides, and those are the sides opposite those corresponding angles. So if I have, let me try to do this a second time. I got lucky the first. All right, pretend those look the same. But if I have a corresponding angle here and here, then this side and that side are not the same size, but they do correspond. And we'll play with that typically in trigonometry quite a bit, but we'll see why we care about that in just a second here. So with these similar triangles, they've drawn it probably much better than I did here. I don't know why I try to draw, because if they have it, I shouldn't. But I have two corresponding angles here. Angle A and angle D are corresponding. They've indicated that with the little angle measure with a 1 tick mark here. But this then side over here corresponds, the segment BC here, the side BC corresponds to the side EF. And they have that probably written, yep, right there. And then likewise, AB is going to correspond to DE, which is what they have here. And then CA is going to correspond to FD, or AC is going to correspond to DF. Now, we can use corresponding sides, corresponding angles in these similar triangles. These guys have to be similar, and these two triangles that they have drawn up here are, because this angle here is the same as this angle here by the interior angles theorem. This one is here because this one here is equal to this one here because we've been told so. And if I have two angles in a triangle that are the same, that third one clearly has to be the same because they all have to add up to 180. So the only way to get these to add up to 180 both at the same time is if this angle here is the same as this angle here. Therefore, they are similar triangles. Right? But the nice part is, and we have to decide where the corresponding angles are. So this angle down here with 2, right here and here. This is so obnoxious that that menu keeps popping up. They have corresponding sides over here. So there and there. So if I'm trying to figure out what X is, this angle with the 1 mark here has this side. The angle, 1 angle mark here has that side. And so I can take these corresponding sides, and the ratio of them is going to be the same as the ratio of every other corresponding side. So that is to say 8 divided by 5, or they've done it the other way, 5. I don't know why they would do it the other way. I'm not going to do it the other way because that's not very smart. I'm going to write that one, 8 over 5, is equal to the corresponding angle or side on this triangle to the corresponding on this one. So the thing that you just have to be careful with is this, let's call this my right triangle. That's a bad word for it. It's not a right triangle. Let's call this the 1 over, I don't know, triangle 2. Let's call it triangle 2 and triangle 1. But triangle 2's values are in the numerators. And angle 1's values are in the denominators. Right? So it has to be angle 2, side from triangle 2 divided by side from triangle 1 is equal to another side from triangle 2 divided by its corresponding side from triangle 1. Right? So that was tricky to say. I don't know why English has left me today, but that needs to be the case. So I can solve this, and the reason that I wrote it the way that I did rather than the way that they did, they're not wrong, but you've got this x in the denominator, which creates an extra step for you. I have an x in my numerator already, so if I want to solve this, I'll solve it over here perhaps. 8 over 5 is equal to x over 7. All I have to do is multiply both sides by 7. All right, so I get 56 over 5 is my x. So 11.2 is my x. All right. So that's and they've done it. They've done their little cross multiplication here. 5 times x is equal to 8 times 7. That's 56 over 5, which is what we got, and then we turn that into 11.2 as well. The Pythagorean theorem says the sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. So that is to say, we have a nice triangle here with 3 and 4 and 5. And you can verify that's true. The square of 4 is actually visualized out here. 4 squared is 16. And then 3 squared is 9. And if you add those, there's 9 here plus the 16. You do indeed get 25, which is 5 squared. Right? But this is true for any right angle, any right triangle. If I have a right triangle in my if I have a right angle in my triangle, then for any of these, a squared plus b squared is going to be equal to c squared. This is one of the most proved mathematical theorems like ever. I think there's a book out there with something like on the order of 2,000 different proofs for this, which is crazy. But if I'm looking at one, I've got a right angle, right? 9 and 12. And then it's always important that C oftentimes is, usually it's a lowercase c. They've written a lowercase c here. That looks like an uppercase C. But it should be a lowercase c on the other side. But that's the hypotenuse. Make sure that you're setting this up right, that it's a squared plus b squared equals c squared, where this c is the hypotenuse, which is the angle across from the 90 degrees. And so if I want to evaluate what C is, I'm going to replace A with 9, B with 12. 9 squared is 81, 12 squared is 144. I add those together to get 225. And I can get rid of this square by square rooting both sides. Square root that, square root that. The square root of C squared is just C, and the square root of 225 is 15. These are called Pythagorean triplets. We had, okay, I lost my pen somehow. We had 3, 4, and 5 in the first example. I have 9, 12, and 15. When I have just nice, beautiful answers like this, whole numbers, these are called Pythagorean triplets. Most of the time, you're going to end up with values that are not beautiful, nice little Pythagorean triplets. For example, if I just have a right angle with 1 and 2, right, then my final answer, I would have 1 squared plus 2 squared is equal to c squared. But 1 squared is 1, 2 squared is 4, and if I have to then take the square root of 5, I don't get a very good answer. In fact, I get 2.236. And this is irrational, so it just keeps going on. 2.2360667, blah, 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 forever, right? So consider yourself lucky if you end up with a Pythagorean triplet, but quite often you won't. All right. So 10.4 is area and circumference. The area is the length times the width. It's the number of little squares that you could stick inside of this thing. If I can, maybe I should have made my squares much larger. But if I can fit 10 squares wide and 3 squares deep, then it's 10 plus 10 plus 10, 30 overall. But area is simply the length of a rectangle multiplied by its width, right? When we start getting outside of a rectangle, we have to get a little bit more creative. But a square is a rectangle with the side is equal to the length. The length and the width are both the same size, and so we call that the side. And so that is still length times width, but each of those is side, so it's just side times side, which is side squared. If I have some wonky shape like this, it's hard to figure out what the area is, but I can turn it into 2 rectangles. I can come in here and cut it, and they've done so here with straighter lines. But I can create 2 rectangles. This rectangle one is 13 feet by 3 feet, and the other one is 6. No, it's not. Make sure you're using the entire length of the rectangle. This is 6 feet plus 3 more, so that's 9 feet by 3 feet. Right? So if I find the area of rectangle 1 has an area of 13 feet multiplied by 3 feet. So 13 times 3 is 39, and I have feet multiplied by feet, so I get feet squared. And if I see feet squared, I know I'm just in area. I know I'm in a 2-dimensional measure here. And rectangle 2 was 3 feet multiplied by 9 feet, right? Make sure that you calculate this side, because they never gave it to you. You had to figure out that this side here was 9 by taking 6 and adding this 3 more to get 9. So it's 3 feet by 9 feet. and that is 27. Again, feet squared or square feet. And then I'll add those two together. 39 feet squared plus 27 feet squared is 66 square feet, or 66 feet squared. The area of a parallelogram we can evaluate by hacking the parallelogram right down off the side. I don't know why I can't make a straight line, but I can't. But I can hack that off and take it and plop it right here. And I've got a perfect rectangle. So the parallelogram is that B length of the base multiplied by the height measured through the material, not the side of this. So it's not this guy over here, it's this height here, right? So you need to figure that value out or have it, right? So if I have this value, and oftentimes they'll give that to you. I've got 8 centimeters in base. This whole thing here is 8 centimeters. The height is 4 centimeters. So it's just that base times height, which is 8 centimeters times 4 centimeters. And that gives me 32 centimeters squared. The excuse me, area of a triangle can also be manipulated in the same way. We're going to use the area of a rectangle is going to be, we'll call it base times height. But I'm going to create my rectangle, if I can, with as straight lines as I possibly can with this goofy little pad that I use. All right, pretend that's a rectangle. But you can see here, this area right here is the same as this area in here. And this area in here is the same shape as this area in here. They're both the same triangle. You can prove that they are similar triangles, that they would have the same area. One is just a rotation of the other. And therefore, if this height of this rectangle is the same as the height here of the triangle, the area of the rectangle would be, that should be an H, base times height. So therefore, the area of the triangle is just half of that. It's half by taking this out and half by taking that out. So it's 1/2 base times height. So then I can say, if I have some some triangle that has 16 and 10, I don't need these measures, right? I don't need to prove this every time. All I need to do is say it's got to be this base times this height and then multiplied by 1/2. So 1/2, 16 for the base, 10 for the height. 16 times 10 is 160, divided by 2 is 80. I've got a meter times a meter, so I end up with meter squared. And a trapezoid, we can play with that just as well, right? I can come and hack off this little bit right here, this little bit right here, right? I can play with those. Essentially, I'm playing with two triangles. So it's going to be half the base times the height for this guy, plus half the base times the height for this guy, right? So I'll have two different ones, and it's essentially just 1/2 A's. We're going to call it, since I can't call them both B for base, so I'm going to call one of them A. So it's 1/2 the area times the height, plus 1/2, not the area, 1/2 the base A times the height, plus 1/2 base B times its height, and they should have the same height, but I can factor out a 1/2 out of both, and I can factor out an H out of both. And so it ends up being 1/2 H times A plus B. So again, if I have such a trapezoid, I can find out its area. We're going to call 46 feet A. We're going to call 32 feet B, and then 13 feet is going to be our H. I don't need these values. I just need those three. And so it's 1/2 times the height times A plus B. So my height was 13. I'll plug that in. A was 46, B was 32, and through the order of operations, I'll let you play with that on your own, add those, and then multiply it by 13 and then 1/2. We end up with 507 square feet. A circle is a set of points on the plane equally distant from a given point, which is called its center. So the circle, again, to my super awesome artistic abilities, is all of those points equally distant away from this point, which we would call the center. Right? Meaning this distance is that distance is that distance is the same as that distance. The radius is each one of these lines is a radius. It's a line segment from the center to any point on the circle. And all radii have to have the same length. Otherwise, it's not a circle. And then a diameter is a line segment through the center. So just right through the center that ends on both sides there of the circle. And it should be twice the radius. If it's not, once again, you don't have a circle. But here I have a diameter, a circle in blue. The diameter is this 40 yard, and the circumference is given by pi times the diameter, or oftentimes you'll see this as 2 times pi times r, because 2r is the diameter. So if I have a diameter of 40 yards, it's pi times 40 yards, or 40 pi yards. Pi is about 3.14 is usually sufficient for us. It's an irrational number that goes on forever. 3.14159276, something like that. But here we've got 40 multiplied by that gives me 125.7 yards, which is to say if I had a diameter of 40 yards on the circle and I was on a walking track and I decided to walk around it, I would go 125.7 yards through one rotation around. Which is the better buy? A large pizza with a 16-inch diameter for $15, or a medium pizza with an 8-inch diameter for $7.50. So what we'd want to do is figure out the cost per square inch of this thing. And they didn't bother giving us, that's cool. So before we do this, let's talk about something else. The area of a circle is pi r squared. Right? So if I wanted to find the area of this, I would have to turn this 40 yards into a radius. So a radius is just the diameter divided by 2. So here my radius is 40 yards divided by 2, so it's 20 yards. So that is to say my area here would be pi times 40 yards squared. And that is $5024. About that. And again, I've rounded pi to 3.14. This should have decimals that go on forever, but we'll round to 3.14 and call it good enough. That's yards squared. So in this example, if I want to find out which one of these pizzas is the better buy, I need to find the cost per square inch. So I've got this 16-inch diameter. So a 16-inch diameter tells me that the radius is 8 inches, while an 8-inch diameter pizza tells me the radius is 4 inches, right? So for the large pizza, my area is going to be pi r squared. So pi times its radius was 8, so 8 squared. That gives me about 201 square inches. Whereas for a medium, if I input 4 inches into its radius, that gives me about 50 square inches. And if I do the cost per square inch, I'll remember these numbers. I don't have to because they're right here. The cost price per square inch is the price of the pizza divided by its square inches. So divided by 201 square inches. So this is about 7 cents per square inch here. But if I look at the medium pizza, it's $7.50 total. And if I divide it by its total square area, then I get 15 cents per square inch. So the better buy, as long as you can eat it all, is that large pizza. And that's it. So hopefully that was helpful. Thank you for being here, and I will see you guys in the course.